Good morning to everyone. This is our fourth lesson of algorithmic design, the second week, and I think that the course is going well, more or less, at least considering the situation. However, I'm trying to move the course to Teams because I think it's a little bit more interactive than YouTube. So I think that we may try to do these moves, this move the next week. So there will be some kind of testing on Thursday, and then we will move there. However, I want to hear your opinion about this move. Okay, as far as the video concerned, for sure YouTube is much better. It's easier to use, the quality is much better, and much better than Teams, of course. However, as I said, Teams has the advantage of being more interactive, namely you can interact with myself during the streaming, and this is a big pro, at least from my point of view. So let me know what you think about this move. So going back to the last week, we were coding the Strassen algorithm for matrix multiplication, if you remember, and I left the coding in the middle of the implementation of the recursive function to compute the Strassen algorithm. So we can go back to the code. This is the code, and okay, and here we are. So many of you asked about a clarification about the parameters of this function, and let me go back just to recap what's going on here. So we are dealing with three matrices, C, A, and B, which are the destination matrix, so the matrix in which we want to place the multiplication among the matrix A and B. Okay. During this process, we are going to deal with many submatrices, and instead of building new submatrices at each recursive call, we are basically using a trick, let's say, and we are basically encoding a frame of a matrix. So a frame of a matrix is what can I call it? It's a kind of view. Namely, instead of building a new matrix, we add two parameters per matrix, which tell us the first row and first column we want to deal with inside the original matrix. Okay, and moreover, we need the size of the submatrix we want to deal with, and in this way we are basically defining a view of submatrix. So we don't need to allocate new space for the submatrix. We are simply dealing with the original matrix, and we are saying, but we are not interested to the overall matrix, but only on the part of the matrix starting from the first row, first column, and whose size is n. Okay, so that's why we have so many parameters in these functions. So by using these tricks, we implemented the computation of both the 10 S matrices and 7 P matrices, and we were left to compute the C subblock starting from the P matrices. So let me see. First of all, we need to compute, we need to compute C11, which is equal to P5, plus P4 minus P2 plus P6. You can see it on the slides. Then we should compute C12, which should be equal to P1 plus P2. Then we will compute C21, which should be equal to P3 plus P4. And last but not least, we are missing C22, which is equal to P5 plus P1 minus P3 minus P7. This is what we saw on the slides, okay? And so how can we do it? Well, again, by using exclusively sums, or better, what we call the function that we call sums matrix blocks and sub matrix blocks for the subtraction among matrices. So first step is to sum matrix blocks, and we want to put the result in C, or better in the blocks 1 1, the top left block of C. So for sure C is the first parameter, and then we need to specify that we want to sum P5 and P4, which are of course part of an array. And so since the array index start from 0, we need to say P4 and let me say here P3. Okay. So you have, with this line of code, we are still missing something here, of course, but with this line of code, I'm going to perform the sum among P5 and P4, and the result should be placed in C. Okay. Now we have to say which are the rows and columns in which we want to place the result. So since we want to deal with the C11, of course, the first row and the first column we are interested in C will be 0 and 0. And this, of course, this is wrong, sorry. Since this is a piece of code inserted inside the recursive call, and here we are, the first row we are interested in and the first column we are interested in inside this call, we have to specify that parameter, so CF row and CF column, of course. Okay. While as far as P4 and P3 concerned, we may specify 0 0, because these are basically submatrix views concerning the whole matrix P3 and P4. Okay. So these matrices are actually not really blocks, but to have a uniform treatment with respect to this function of all the parameter, of course we need to insert something here, and so we want to say that we are interested in dealing with the whole matrix. So the first row and first column we are dealing with in P4 and P3 are 0 and 0, of course, and the size of the matrix we want to deal with is N2, which I recall is basically N divided by 2. Okay. Now we are missing the subtraction part, so let me go here. So now in C11 we have P5, P4, we have to subtract P2, so let me write here P1 because of the things we said before. So the array index start from 0, so P2 is actually P1 in our code, and vice versa, of course. And we want to subtract from P11, we want to subtract P2 from C11, which is the sum among P5 and P4. So the second parameter should be C right now, and of course we want to change the first column and first row and first column and the second parameter too. So this is the change that we need to make. Oh, by the way, this should be a sub, of course, and this is it. So let me change here. Okay, so to be consistent with the typecast, and of course we are missing to some P6, so let me go back here. I basically copy this part of the code, I'm summing up things, and now in C11 we have P5 plus P4 minus P2, so we have to sum up what's in P11 with P6, and this is done in this way, of course, and this is it. So now in C11 we got exactly what it is written here. Okay, so hopefully this is what the Strassen algorithm should do. So what about this piece of code? Well, again, this is quite easy. We can simply place in C P0 plus P1, and however here we are dealing with the subblocks 1, 2, so here we need to sum up 2. Okay, and as far as the P arrays are concerned, again we are still preserving the first row and first column, and this is it. Now again, so let me do everything, but I mean it's quite straightforward once you have understood this part of the code. So we should be 2, we should be 3, and here we are dealing with C21, so this should be plus N2, and this should be 0. Okay, and this is it. And going back to C22, so let me copy what we did before, just because I'm lazy. I don't want to write everything from the scratch. So this should be P4 plus P1, so this is it. We need to subtract P3, so this is a subtraction, this is correct. P3, here we are, and this is it. And then we need to subtract P7, so this should be 6, it should be a subtraction, and everything should be fine right now. Okay, now this piece of code basically complete the computation of C, okay, and we are missing one little thing. So as you see here, we allocated matrix, and we allocated also the arrays containing referring to the matrices. So we need to deallocate all this stuff, otherwise it would be a memory leak. So let me remove this to be continued, and so let me copy it. Again, I'm lazy, so I don't want to waste my life in remembering what's going on up there. And okay, so first thing to do is to call the allocate, which is a function already developed here, the allocate matrix, which takes the address of the matrix we want to allocate and the number of rows of the matrix itself. So here we want to deallocate as I, and the number of rows is of course n2, and we need to free s. Okay, this is it. And what about p? Well, more or less is the same. So let me do it a little bit here. Free s. This is it. Oh yeah. Someone is saying that I missed to change the first row and first column in C22, and you were right. So it should be seen plus n2 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 and plus n2, and finally plus n2. Okay, this is it. Thank you. As you see, being lazy is not the best thing to do always. So this is it. Now we are left with the call to this function. So now we have implemented the Strassen auxiliary function. So let me copy its signature, because we have to call it from this function, which basically hide the details of the API, because this is an internal API, let's say, while the signature of the Strassen matrix multiplication is an external, meant to be used from users, let's say. So this is quite easy to achieve. So we want to multiply A by B, and we want to place the result in C. And since this is the very first call, we want to deal with the whole matrices. So 0 0. Let me go back. Let me go back here. 0 0 again, and 0 0, and finally n, which is the last parameter of the Strassen matrix multiplication function. Okay, so this is it. This is the implementation of our function and of the Strassen algorithm. Okay, so let's test it. Let me open the terminal, go into Strassen directory. Here I can compile it. This is the result, and let's see what's going on here. I recall the fact that here we are seeing the execution time for a specific size of the matrix, and for both Strassen and naive algorithm. Okay, so here you can see that there is something weird happening, because the Strassen algorithm takes our implementation of the Strassen algorithm takes much more time than the naive algorithm. So some of you may wonder if we waste our time, and the answer is of course no. Okay, I don't like, as I said, I'm lazy. I don't like to waste my time. So what's going on here? Well, the point is that we proved that the Strassen algorithm is better from a symptotic point of view with respect to the naive one. Okay, so this doesn't mean that for any instance of the problem the Strassen algorithm is better than the naive one. There are instances of the Strassen algorithm for which the overhead due to the matrix we need to allocate to compute the result, the recursive calls, and so on and so forward, is too much. Is too much with respect to the naive algorithm. So the overhead due to all our computations is really too much to be competitive with the naive algorithm. Of course, there will be a size of the matrix for which the Strassen algorithm, our implementation of the Strassen algorithm, will be better than the naive algorithm. Okay, but as you can see here, up to 1000 rows and columns, the naive algorithm is much better than the Strassen implementation we did. So what can we do? Well, the point is that, as you can see here, for instance, in these two lines, let me stop the code because it's basically useless. As you can see here, the growth in terms of execution time of the Strassen algorithm from 512 to 1024 is basically more or less, let's say, 9. Okay, so you see, if I divide the execution time due to matrix multiplication whose size is 1000, more or less, by the execution time due to the matrix multiplication among matrices whose size is half of 1000, I end up with 9. Okay, while if I'm trying to do the same thing here, well, so with the naive algorithm, I end up in discovering that the naive algorithm grows much faster than the Strassen one, which is not really surprising because the naive algorithm is cubic while the Strassen algorithm is subcubic. So, however, this tells us something about how to improve the algorithm because we may basically figure out that the problem with the Strassen implementation we did is the basic case. So in our implementation of the Strassen algorithm, we decide to place as basic case n equal to 1, but this is, our choice. And if you remember, I'm going back to our code here. In the basic case, we decided basically to apply the naive algorithm. Okay. So what if we try to reduce the overhead due to the fact that we are dealing with so small matrices? And basically, what if we decide to take as basic cases something which give us some advantage in terms of growth? So let's for instance focus on this part of the diagram of the table. As you can see here, we have a growth which is more or less 1/8. Okay, so moving from 128 to 256 grow the execution time by 8 in naive algorithm, while here the growth is smaller. Okay, for sure, if we multiply 3.032 by 8, we end up with something smaller than greater than this number. So it could be a good idea trying to say, okay, if my matrix is too is small but not too small, so smaller than smaller or equal to 128, we end up with the naive case, okay, with the naive algorithm. So let's try to make this change, which is quite straightforward. So if n is smaller or equal to 128, this is the change. Let's try to compile it. Okay, and execute the code. And suddenly we end up with a code with an implementation of the Strassen algorithm which is much faster than the previous one. And as you can see here, for instance, in the previous implementation, multiplying two matrices whose size is 1000 takes 93 seconds. Here takes 0.93 seconds. Okay, so it's a huge improvement. Still, the Strassen algorithm is more than quadratic, of course, but we reduce the constants. Okay, and so this is a good choice, at least from the point of view of the matrices, of the small matrices. Okay, and this is it. So so right now we have an implementation of the Strassen algorithm which is better of the naive algorithm for matrices whose size is greater than 128. And I left you as homework to generalize the Strassen algorithm to matrices whose size is different from the power of 2 and to matrices which are not square matrix. Okay, and this is it. So if you have any comment concerning the Strassen algorithm and what we saw, it is welcome. Okay. Oh, by the way, since as you can see here, we have a huge improvement. Okay, so but we have an improvement of more than 10 times in execution time of the Strassen algorithm implementation we did with respect to the naive one for matrices whose size is 2000. And you will see that if you left the code go on, of course the difference will increase. Okay, so someone is asking why the Strassen algorithm improve a lot even when n is greater of 128. Well, the answer is that what we saw before. So the problem with the Strassen implementation we did before is due to the constants. And by saying, okay, I don't want to keep building up new matrices, I don't want to keep applying recursive call under 128, we reduced that constants. Okay, and by doing so, we were also able to reduce the execution time. And that's the point. Okay, so the point is, here is our computation, our recursive calls stops when n is smaller than 128, smaller or equal to 128, and this helps us in avoiding the allocation of new matrices and so on and so forth. So it's just a constant improvement, let's say. So we divided the execution time by a certain number, but this is enough to bypass the complexity, the execution time of the naive algorithm. So, okay, I hope so. So, as I was saying, many of you were concerned about the parameters in the Strassen auxiliary functions and Strassen auxiliary function and in the naive matrix multiplication and so on and so forth. So I decided to implement a different version of the Strassen algorithm, and you can reach it by pulling from the Git repository the last version of the code and going to a different branch, which is the more structured branch. So this branch report a different version of the code, and let me go there just for the sake of clarity. So check out more struct and okay. Let me go back to the last version. Okay, and let me just make some comments about this version. So this version is basically a version in which I define new type, which is some matrix type, which is a view of the matrix, and inside the structure I'm placing the first row I'm interested in, the first column I'm interested in, the matrix itself, and the size of the submatrix I want to deal with. At this point, every signature, so all the signatures of the function we implemented are much easier to understand. So I want to subtract submatrices, and in particular I want to subtract submatrices A and B and place the result on submatrix C, and so it's easy to figure out what's going on. And this is done also for the naive matrix multiplication and the Strassen algorithm, as you can see. Okay, so this is the best thing to do if you are trying to implement the code in a more structured way. And for instance, it would be my choice if we were developing the code in C++, because of course I can also override the index function, and so for instance I can sum up the element of the submatrix A and the element of the submatrix B in much easier way. Let's say, instead of remember that I need to sum up the index Y to the first row of A and so on and so forth. Okay, and this is it. So if you were concerned about the parameter of the function that we implemented during the lesson, please have a look at this on this code. Okay, and by the way, as you probably already noticed, I also added another branch in the repository, which is the final one, which contains of course the final version, of our implementation. Okay, so I already did it, and by the way, I added also some comments on the code, so it's much easier to figure out what's going on. This is it. So any question about the matrix multiplication? Okay, if you don't have any other question, I think we may go on. By the way, I'm leaving the code running here, as you can see, and we are still waiting a result of naive algorithm on multiplying two matrices whose size is 4000. Okay, while the Strassen algorithm already ended, and take the multiplication on the Strassen, on our implementation of the Strassen algorithm takes 45 seconds. Okay, so this is it. Let's move to the next topic then. Okay. Oh, this wasn't meant to be here. This is it. Not really. Okay, this is it. So the next topic is the matrix chain multiplication. So it's somehow related to what we saw until now, and namely we are dealing again with matrix multiplication, but this is quite different problem, quite different approach, and that's why I want to go through it. Okay, so first of all, of course, we need to define the problem, and to define the problem, let's have a look to a small example. So let's consider three different matrices having different dimensions. Okay, so A1 have a dimension 55, so 50 rows, 5 columns. A2 have dimension 5, 100, so 5 rows and 100 columns. And finally, A3 have dimension 110, so 100 rows and 10 columns. So how many scalar multiplication, so how many multiplication among numbers, let's say, are required to compute the matrix multiplication A1 times A2 times A3? Okay, so the problem is, rather clear, nothing special, quite easy to solve, right? Let's see. So the matrix multiplication is associative. This means that we can obtain exactly the same result by first of all multiplying A to A2, A1 to A2, and multiplying the result by A3, or first of all multiplying A2 by A3 and then multiplying the result, and then multiply A1 by the result. Okay, so this is clear. Now let's have a look to the number of multiplication required to perform the first operation, so multiplying A1 by A2 and then result to A3. So if we perform this kind of, if we use this parenthesization, we end up in doing the following number of operations. So since A1 has size 50 times 5, okay, so 50 rows and 5 columns, while the matrix A has size 5 rows and 100 columns, the number of element in the resulting matrix is of course 50 times 100. Okay, so A1 times A2 is a matrix having 50 rows and 100 columns. Okay. Now, if you remember the matrix, the row column multiplication, of course, once we have selected the row of A1 and the column of A2, we have to go through all the elements in these two rows and columns. So for each element in the resulting matrix, we have to perform 5 multiplication, which is the number of columns of A1 and the number of rows of A2. Okay. So to get what is inside this parenthesis, we need to perform 25,000 multiplications. What about multiplying what's inside this parenthesis to A3? Well, what's inside this parenthesis again has size 50 rows and 100 columns. So while what is A3 has a size 100 rows and 10 columns. So the result of this multiplication is a matrix whose size is 50 rows and 10 columns. Okay, and to get each element inside this matrix, we need to perform 100 multiplication. Why? Because the number of columns of this matrix is 100 and the number of rows of this matrix is 100. Okay, so this means that just to multiply the result of what's inside this parenthesis and to A3 require 50,000 multiplications. Okay, scalar multiplication. So in total we end up in requiring 75,000 multiplications. Okay, what about the other parentization? So what's the number of multiplication, scalar multiplication, so multiplication among number required to compute A1 times parenthesis A2 times A3? Well, in this case you can perform all the computation. The number of scalar multiplication required is much less, and in particular are 7,500. So we decrease by 10 the number. Simply by changing the parentization, we decrease by 10 the number of scalar multiplication required to perform this operation. Okay, so let's try to define the problem in a more general way. We understood that depending on the parentization, the number of scalar multiplication required to perform the overall multiplication of the matrices decrease or increase. Okay, so change, and so let's try to formulate the problem in a more general way. So let's consider the case in which we have a chain of matrix, so a sequence of matrix A1 an, a sequence of matrix which should be also compatible, namely for every I in the sequence, I should be able to multiply AI by AI plus 1, of course. Okay, and this condition is basically written here. So for every AI, the dimension of AI should be this one. Okay, so pi minus 1 is the number of rows of A1. Pi is the number of rows of A plus 1. Okay, so this is it. So the problem now is to compute a parentization with minimize the number of scalar multiplication to compute the overall multiplication of the matrix in the chain. Okay, so we want to minimize the number of products among numbers. Okay,
So let's try to solve the problem in a naive way as usual. So a possible solution would be to search the best solution, well, a minimizing solution among all the possible parenthesization. Now let's try a recursive approach to compute all the possible parenthesization. So if n is equal to 1, so if the number of matrices in the chain is 1, well, the parenthesization is obvious. Of course, we don't need to do anything. It's clear what's going on. Okay? Now, if n is greater than 1, we can parenthesize the chain as we are seeing in the slides for every k. So for every k between 1 and n minus 1, we can decide to say, okay, all the matrices between 1 and k should be placed in the same parentheses, and all the matrices from k plus 1 and n should be placed in the same parentheses. Okay? And this is a way of parenthesizing. Of course, this holds for every k. Okay? And recursively we may compute the parenthesization for a1, ak, and ak plus 1 and an. Okay, in this way we are able to produce all the possible parenthesization for this chain. Now the problem is, how many parenthesization are we going to produce? Any guess? I don't know if you have any guess. Anyhow, let's try to figure out a possible number for this number of parenthesization. So let's say we want to compute the number of parenthesization for a chain of size n. Okay, so we already know that is 1 if n is equal to 1. Okay, now if n is different from 1, as already shown on the slides, we may split the chain in two different subchains for every k going from 1 up to n minus 1. Okay, so for every possible k going from 1 up to n minus 1, and now we have to compute, once we have selected the k, we have to compute the number of parenthesization. Okay, so let's assume we have fixed the first part of the chain of subchain. Okay, so we have fixed k, and we have already selected a parenthesization for the first part of the chain itself. So we are left to select a parenthesization for the last part, but since the last part is a chain again, the number of parenthesization can be computed as p of the size of the subchain. Okay, so once I have the first part, the number of parenthesization is equal to p of the size of the second part. Okay, and the second part has a size n minus k. Of course, this holds for every possible parenthesization of the first part. And how many parenthesization of the first part we have? Well, of course, again, we can use p to compute the number of parenthesization, since the the number of elements in first part of the array for sure is smaller than the number of elements of the overall array. So this is pk multiplied by pn minus k. Okay, and this is the number of parenthesization that we have for a chain of sizes n. Let me write if n is greater than 1. Okay, now as usual, here we have a problem because we have written a correct equation for sure, but we don't know what's going on here. So what if you want to build up a closed version of this function? Namely, we want to remove the recursion for the function itself. And we also turn the different matrices to a mid-man. Let me go back to some of your questions. We should also take into account the dimension of different matrices admit to made matrix multiplication, isn't it? Yes, but we did it in the definition of the problem. So in the definition of the problem, we already said that all the matrices are compatible for the matrix multiplication by writing this stuff. Okay, so here I'm saying that the number of rows of A1 is pi minus 1, and the number of columns of A1 is pi. So the number of rows of A plus 1 is pi. Okay, and so AI and AI plus 1 are compatible and can be multiplied. Okay. So what does Pn means again? So Pn is the number of parenthesization possible for any chain matrix whose size is n. So in this case, n is this number. Okay. So we are having a chain of matrices whose size is n. How many possible parenthesization do we have? It does count the size of the matrix yet. Well, we are just counting the number of parenthesization. So in the number of parenthesization, we are not taking into account the size of the matrix themselves. Okay, so we know they are compatible. So we know we can multiply them, but we are not evaluating the number of products. We are simply evaluating the number of possible parenthesization we have. Okay, so in how many ways can we associate the matrix so to deal with at most 2 matrices per time? Okay, and here we have okay, let me I missed to change the slides again. So here we are. So here we are. As I said, let me go back. So P is the number of parenthesization, N is the size of a chain matrix, and since we are saying here that A1 has dimension as number of rows pi minus 1 and number of columns pi, AI is compatible with AI plus 1. So I can multiply AI to I plus 1. Okay, this is by the definition of the problem, and this is it. So let me go to the tablet. Here we are, and the tablet is here. Okay, And again, here we are simply counting the number of possible parentization, not the number of scalar multiplication we are doing, okay, to solve the problem. We are counting the number of possible parentization because remember, our first try to solve the problem was to produce all the possible parentization and then extract from them one which minimizes the number of scalar multiplication. To do it, we have to produce all the possible parentization. So let's first of all try to count them. And so this is P. So P is the number of the number of possible parentization and so on and so forward of A1 A. Okay. And this is it. So now let's try to figure out a possible closed formula for Pn, because here we have a recursive version. How can we do it? Well, let me just try to write this part extensively. So this is so I'm basically unroll this sum, and this is P1 multiply by P n minus 1, okay, plus so on and so forward. So this is equal to plus and here we will have the last term, which will be P which will be n minus Pn minus 1, because k reaches n minus 1, multiplied by P n minus 1. Okay, so let me go to the next slide. So let me delete it. So for sure that one will be greater. For sure that one will be greater or equal. So let me go back for a while. Notice that this is equal to this one, okay? Because if I simplify the last term of P, I end up with 1, and of course multiplication is commutative, so this one and this one equals. So for sure all the terms in that sums should be greater or equal than 2 multiplied by P1 multiplied by P n minus 1, okay, which of course is equal to 2 multiplied by P n minus 1, because we saw in our definition that this is equal to 1, okay. So now we prove that Pn is greater or equal to 1 if n is equal to 1, or to 2 Pn if n is greater than 1. Okay? Now guess what? This new formula, this new disequality is much easier to understand. What about all internal dandy? So you were saying, some of you is asking what's going on with everything here. Well, I simply forget them. I'm just saying that this sum is greater, let me see here, is greater than this one. Okay, so since it's greater, I don't care about them. I'm simply want to reduce all the property to reduce P to this inequality. So this inequality is much easier to be solved, okay? Because for sure, if it's wrong, by the way. No one notice this. This is the correct equality, of course, and so as I was saying, this is much easier to be solved, because basically I'm keeping multiplying by 2 every time I decrease n by 1. Okay, so guess what? Here I can say, since because of this inequality, I can say that Pn belongs to big omega of, guess what, 2n. Okay, so this is just to say that the number of possible parenthesization is exponential in the number of elements in the chain, which is awful. So to solve the problem in the naive way, we have to compute an exponential number of possible parenthesization, and this is just to compute the parenthesization, not even to compute the number of matrix multiplication we are required to perform. Okay, so this is not really an acceptable solution. And let me go to the slides somewhere here we are. Okay, so how can we solve the problem? This is naive approach we already saw, and this is what we saw on the whiteboard. So how can we solve the problem? Well, to solve the problem, we have to observe two important things. First of all, if of some kind of our computation we end up in concluding that the parenthesization you are seeing on the slides is optimal for the chain, so the best thing is, a certain point of the computation is to split the overall chain into two subchains, A1 AK and AK plus 1 AN. Then in this case, for sure, the first parenthesization is optimal. So the parenthesization get here should be optimal also for the overall chain, and the second parenthesization should be optimal also for the overall chain. If this is not the case, well, you can get a better parenthesization simply replacing the parenthesization you got here by the new optimal parenthesization. Okay, so the point is, we can split the overall computation of finding an optimal parenthesization for the chain of multiplication simply in sub-problems. Okay, now the problem is now how to get k, so how to decide that this is an optimal parenthesization. Okay, but we will see later on. Another breakthrough observation is that many of the recursive call we need to perform to evaluate this optimal parenthesization are basically the same. So let's consider the case in which, for instance, you are decided that k is the best way to parenthetize a1 an. Okay, so for every possible parenthesization of a1 ak, you have to recompute all the parenthesization of k1 plus ak plus 1 an. But of course they are always the same. Okay, so once you have computed the parenthesization for the first part, you can store basically all the results, all the intriguing results, all the interesting results, and avoid to recompute all of them every time you need to compute a new parenthesization for the second part. Okay, and this is it. So the idea is to use what is called dynamic programming. So what's dynamic programming? Dynamic programming is a technique which is meant to reduce the number of recursive calls simply by storing or memoizing, how it is called, not memorizing but memoizing the result of the previous recursive call. Okay, and since we know that many of the possible recursive calls are basically already solved the previous computation, we end up in what would be a sub exponential solution. So let's see a dynamic programming solution. So the idea is to store the minimum products for all the subchain in M. Okay, so M is a matrix which basically store all the possible minimum products for the matrix going from I to J. So what's the element ij in M? The element in ij in M is the number of products required to compute the minimum number of products required to compute the chain matrix multiplication of the matrices between AI and AJ. Okay, great. Now, of course, we can define it recursively, and this is quite clear. So if I is equal to J, so if I'm dealing with exclusively one matrix, the number of product required to compute the matrix itself is 0. Okay. Now, what about the case in which I is smaller than J? Well, in that case, we have to decide where to place K. So how to parenthetize at the first level the chain AI AJ. So where to place the first parenthesis, okay? And this is what we are going to minimize. Well, for each of the possible K, so for each of the possible first level parenthesization, we are computing the minimum number of products required to perform that parenthesization, simply summing up the minimal number of parenthesization for ik, so for the subchain going from I to k, plus the minimal number of products required to perform the chain matrix multiplication among a k plus 1 aj. Okay, and this is given basically by recursion, plus what? Plus the number of matrix multiplication required to multiply the first part of the matrix, so the result of the first sub chain matrix multiplication times the result of the last time chain matrix multiplication. So let me again go back to the whiteboard to see what's going on. Okay, and let me see. Okay, so let's assume we are dealing with A1, AK, AK plus 1 and AN. Okay, this is our chain. Okay, and let's assume that we have fixed one possible first level of parenthetization. So we decided for some reason to parentetize this chain in this way at the first level. Okay, now let's try to compute the number of matrix multiplication required to perform this operation, this overall operation. So this matrix chain matrix multiplication. So it would be the number of let me call number of matrix, sorry, not matrix but scalar multiplication so number of matrix multiplication, let's say m, so m1 n, because I'm dealing with this instance of the problem, will be equal to what? Well, the number of matrix multiplication required to perform the evaluation of this subproblem, which will be m1k, plus the number of matrix of scalar multiplication required to solve this subproblem, which of course will be mk plus 1 n. Okay, and now we have compute, let me call it a1k, and this will be a k plus 1 n. Okay, so these are two new matrices. Let me write in this way. Okay, now we have to add to what we wrote here. We have to add the number of scalar multiplication required to perform this operation, so the multiplication among this new matrix with this new matrix. And since the number of number of rows in this matrix will be P1, we can write P1. The number of columns in this matrix will be Pn, of course, and the number of columns in this matrix will be the number of columns of this matrix. Okay, so we can write Pk. Okay, and this is the total number of possible total number of scalar multiplication required to perform the chain matrix multiplication having this parenthesis. Of course, there are n-1 possible different parenthetization, first level parenthetization. So this case can range from 1 up to n-1, and we have to minimize it. Okay, and that's why here we have the minimum. Okay, and please notice that this equation is more general than the one we saw on the whiteboard, because here we are dealing with index ranging from I to j, while in the previous equation we were dealing with an index ranging from 1 to n. So this is more general. That's why it seems a little bit more complex, but actually it is not. So okay, so this is the So M stores the minimum number of products for all the subchains in M, and we can compute recursively in this way. And we need for sure another matrix called S that basically store these values. Okay, so let's see what's going on. Consider an example just to figure out how all this stuff work. So let's assume we want to multiply A1, A2, A3, and A4, and their size are the one you can see on the slide. Okay. Now this is M and this is S. Now we want to compute. First of all, we want to compute of course the minimal number of parentization to perform the chain matrix multiplication from 1 up to 4. Okay, so we want to compute this number. Okay, and this is what we are doing. We want to compute this number. Now, to compute this number, we first may try to compute the first level parentization of this overall chain, and this is done by selecting as first possible choice k equal to 1. So at the first level we have a parentization in which the first submatrix is exclusively A1 and the second submatrix is built from A2 up to A4. Okay, and this parentization corresponds to this cell, because we are this second parentization, so this second subchain corresponds to this cell, because this cell contains should contain the minimal number of scalar multiplication to compute the submatrices going from 2 up to 4. Okay, and while this parentization, the number of scalar multiplication required to perform this parentization, of course, is contained here. And since we are dealing with a single matrix, the number of scalar multiplication is 0. Please notice that at the beginning of computation, all the elements on the main diagonal is set to 0, because they represent the minimum number of scalar multiplication required to perform the scalar multiplication, to solve the chain matrix multiplication between an and an. Okay, so these cells represent basically the chain matrix multiplication instances having one single matrix, and of course the number of scalar multiplication are 0 to perform a matrix multiplication of a single matrix. Okay, now here we are dealing with this sub-problem, and this sub-problem can again be split into sub-problems. The first one in which we have a single matrix, and the second one, second sub-problem, dealing with two matrices. Okay, so this is the cell representing this sub-problem, and this is the cell representing this sub-problem. Okay, so again, this cell contains the number of matrix multiplication required to perform to solve this chain matrix multiplication instance, while this cell represents the number of scalar multiplication required to solve this chain matrix multiplication instance. Okay, again, this instance of the problem can be split in two different subproblems. The first one having one single matrix, and the second one having again one single matrix, as we saw it, and as we see it, and so right now we can perform backtracking, because we know that this problem takes time this problem can be solved in performing zero scalar multiplication. This problem can be solved in performing zero scalar multiplication. So now we need to compute the overall time to perform the external, let's say, sub-problem. So the one dealing with both A3 and A4, and this is easy to compute because we know the number of rows in A3, number of rows and columns in A3, and number of rows and columns in A4, and this can be done by multiplying the number of rows of A3 by the number of columns of A4 by the number of columns of A3 again, and this is 60. Why? So the number of rows of A3 is 10, the number of columns is 2, the number of column of A4 is 3, so 10 by 2 by 3 is 60, okay? So now we can fill it, and by filling it we know that the correct choice of k, so the best k, the k that minimizes the solution of this sub-problem is 3. Okay, in this case it's easy, of course, because we only had two matrices, but still we can store it. Okay, and the best way to solve this simple instance of the chain matrix multiplication problem is to select 3. Okay, and that's why we as k. Okay, and that's why we put a 3 here. Now we can try to solve again this problem, and to solve this problem we need to, okay, right now we know the solution, so we know how many scalar multiplication are required to solve this problem. We know how many scalar multiplication are required to solve this problem. So we need to sum up this value with the value corresponding to minimal number of scalar multiplication required to solve this problem, so 60. And then we need to sum up to this sum also the number of scalar multiplication required to perform this matrix multiplication, which is 5 times 10 times 3. Okay, and here we are. Okay, so why this is not written in bold? Well, this is not written in bold because this is and the same here, because please notice here I put a 2 because I was dealing with parenthesization in which our k is now 2. Okay, so the level parenthesization was made up to now by selecting 2 as a possible candidate for k, so as possible candidate for the best parenthesization for this instance having 3 elements, and that's why I wrote 2 here. Now, why these two numbers are not in bold? Well, the point is that they are not final result. This is not a final result because I only tested this value for k, but of course there may be a different parenthesization which may be better than the one we just tested. So for this system, the problem, sub-problem dealing with A2, A3 and A4, I only tested the parenthesization in which A2 is alone and A3 and 4 are placed in this way. But of course, I may change the parenthesization for this sub-problem. I may try to see whether a better parenthesization is the one in which I place A2 and A3 all together and I left alone A4. Okay? And so this sub-problem, so the minimum number of possible parenthesization for A2 and A3 can be obtained by looking at this cell. Okay, and if I do so, again, I can split this problem into sub-problems, the one dealing with exclusively A2 and the one dealing with exclusively A3. and I know the number of matrix multiplication required to solve these two simple instance of the problem, so I can compute the minimal number of matrix multiplication required to solve this instance of the problem. So the instance of the problem in which I'm dealing with exclusively with A2 and A3, and this is 100. Why? Because A2 has 5 as number of rows, 10 as number of columns, and A3 has 2 as number of columns. So A5 times 5 times 10 times 2 end up with 100, and this is the final number of possible this is for sure the minimal number of possible minimal number of possible or required scalar multiplication, because there are another. This is the only way in which I can split this problem into sub-problems. So no other possible sub-parenthesization is possible for A2, A3. Okay, so that's why I place here the number 100 in bold, and of course I can place in S number 2, saying the best minimal parenthesization for the sub-problem starting from the second matrix up to the third matrix is by placing the parentheses in the second position, so here. Okay, and so here we are. So all the possible parenthesization for the sub-problem dealing with A2, A4 have been performed. So this is the last one. So it's not possible to reducing the problem with 3 matrices in different way. So all the possible sub-parenthesization for the 3 matrix instance we see here have been considered. So I can compute right now the best among all we saw. So up to the previous step, the minimal number of possible parenthesization for A2, A4 was 210. Now, since I discovered that I'm able to perform the minimal matrix multiplication among A2, A3 with 100 multiplication, I can compute the minimal number of matrix of scalar multiplication required to perform A3, A4 by using this. By using this parenthesization, which is 130, and this is the last one. So we discover all the possible parenthesization for this sub-problem. Of course, if I go on, I basically able to fill up all the numbers in the 2 matrices. Okay, and I'm able to perform to figure out the best parenthesization, which is the one we see here. Okay, so if I want to compute to solve the chain matrix multiplication instance dealing with these 4 matrices, so looking at the top right position of the matrix S, I discover which is the best case to parenthesize at the first level the largest instance of the problem. So the original problem. So the one dealing with all the 4 matrices. Okay, and this number 3 tells me that this is the best way to parenthesize at the beginning. Then, since I decided to parenthesize the overall problem in this way, which is the one which minimizes the instance of the problem, the number of scalar multiplication, I need to figure out how to parenthesize A1, A3, and this is done simply by looking at the S matrix again. So by looking at the S matrix again, I can discover the fact that A1, A3, which is the cell denoted by row 1, column 3, can be parenthesized in this way. Okay, So this is the best way to parenthetize this subproblem. And this is done by placing the first parenthesis at the closure of the first parenthesis at matrix 1. Okay. And of course, I'm left to discover how to parenthetize this one. Well, this is easy because they are two. But if I want to go on, I need to look at let me see 2, 3. This number. Okay, here we are. And so right now I know that this is the best parenthesization I can get from the point of view of the minimal number of scalar multiplication to solve the problem. Okay, this is it. Of course, well, this is a recursive process. We saw a recursive process, but it's easy to perform it from an iterative point of view. So starting from the scratch, as we saw it, I can keep evaluating the diagonals without starting from avoiding recursion, basically starting from the main diagonal and moving to the right top of the matrices. Okay, easy. This is the pseudocode. I don't want to go through it because it's quite easy, and I mean, just have a look at it. By looking at the code, we end up in discovering that, okay, this is the code, in discovering that the computation takes time, theta of n cube. Please have a look at the calculus concerning the computation, but I mean, it's not that easy, that difficult to understand. Okay, so this is it. So now we were able to solve. We started from the original problem, which is the chain matrix multiplication problem. We discovered that trying to enumerate all the possible parenthesization is not possible because we end up with an exponential algorithm, and we discovered that by using dynamic programming we are able to perform a very same task we target at the beginning simply by performing a theta of n cube algorithm. Okay, why so let me go back to your question just to understand what's going on. Some of you ask, isn't cell adjacent to another value, another cell? So let me see here. Okay, so some of you is asking, here we have two cell containing, so two different parenthesization containing 130. Okay, so is arbitrary to decide which one is the best one. I mean, there isn't a best one. Okay, so why we decided to go in that direction instead of the other one? Well, it's up to you. We want to find a possible parenthesization which minimize the number of scalar multiplication. We don't want the parenthesization which minimize. Okay, so there may be many possible parenthesization minimize the number of scalar multiplication, but we want to return just one of them, and that's the point. Okay, I hope I answered your question. I hope so, at least. Again, feel free to send me an email with more question, or write on the comments below the video. And I'll try to answer to all your questions. Okay. well, and this some of you is asking why there are two different cells and the result doesn't matter. Well, the point is that in this particular case we have two cells and two cells whose value is the same, and it doesn't matter whether I choose one of them. But there may be cases in which make the difference. Okay, so the point is we just want to return one possible parenthesization. It's not guaranteed that there is only one, and for sure, well, one of the possible problem is that there isn't just one of the possible parenthesization. Okay, this is it. So as homework, as I already said, you can find the homework on Moodle, and was related to the previous lesson. So it's about to improve the efficiency of the Strassen code we saw, and let's try to solve it. Okay, I hope you enjoy this algorithm, because probably is quite interesting from a theoretical point of view, at least, because give you the chance to investigate why dynamic programming is so interesting. So we started from an exponential space of possible solution, and we discovered where we can browse all of them in a cubic algorithm, simply by observing that many of these possible solutions can be split. Well, all these possible solutions can be split in sub-problems which are basically identical for many of them. Okay, and this is it. Okay, so I hope you enjoyed this lesson, and we will see you tomorrow for the fifth lesson. Let me know what you think about the course, and any comments again are welcome. Okay, thank you so much, and see you tomorrow, hopefully. This is not, I'm missing the, okay.